Hey everyone, and welcome back to the fourth installment of our Introduction to Counting and Probability video series. In today's video, we'll talk a bit about advanced counting strategies, which include casework, complementary counting, constructive counting, and counting with restrictions.
Since we have a lot of material to cover today, we'll need to move faster than we usually do. Feel free to rewatch this video multiple times in order to fully comprehend what we talk about. Let's first start with casework.
You've probably used casework before. As the name implies, casework allows us to break up a larger problem into easier subproblems. However, we must remain organized with our casework to ensure that we don't forget any cases.
Since we enjoy learning by solving problems, we'll apply that strategy today. Thus, we'll quote a problem from Introduction to Counting and Probability, written by David Patrick. Specifically, problem 2.1 of section 2.2, which exhibits the strategy very well.
The figure to the right represents a road map between four villages, labeled A, B, C, and D. The arcs indicate paths between the various villages. How many ways are there to go from A to D along the paths if you can only move left and right? For example, you can't go ABA, BACD. You can only go ACD or ABD.
It's clear that casework is our best bet. We know that in order to get from A to D, we must either pass through B or C. Choosing between B or C is an exclusive situation, since we can either choose one or the other.
Thus, we have two cases to consider. We either take the path ABD or ACD. For the path ABD, there's 4 ways to get from A to B, and 3 ways to get from B to D, since the choice of path made to get from A to B is independent of the choice of path made to get from B to D. Hence, we multiply 4 by 3, giving us 12.
We repeat a similar idea for the path ACD. There's 2 ways to get from A to C, and 4 ways to get from C to D, leaving us with 8 ways to get from A to D through C. We will add the answers we get for each case, since the path ABD is independent of the path ACD. Hence, 8 plus 12 is equal to 20.
That was a fun problem to gain some intuition about casework. To test your understanding, we have a fun problem for you to solve. We will also provide you a hint so you can establish the connection between our path problem and this problem. This is problem 2.3 of section 2.2. How many pairs of positive integers, m, n, satisfy m squared plus n is less than 22?
Hint: set bounds on the value of m. What value is m forced to be less than?
We can now segue into our discussion of complementary counting. Complementary counting, we subtract the cases in which an event that we don't want to occur can happen from the total number of ways a given situation can occur.
Let's study complementary counting with a problem. Our problem is actually from section 2.2, which you may recall is about casework. You'll find a second, simpler way to approach this problem using complementary counting. The inhabitants of the island of Mumble from Palm 2.2 decide to expand their alphabet to the standard Roman alphabet, 26 letters A through Z. But they still limit their words to 3 letters or less. And for some reason, they insist that all words contain the letter A, at least once. How many 3-letter words are possible?
Rather than using casework based on the number of A's in each word, we'll subtract the number of ways we can create a word with no A's from the total number of ways we can form 3-letter words normally, assuming we're using the Roman alphabet, which we are.
There's 26 to the 3rd ways the Mongolians can create 3-letter words, with no limitations, as each letter in the word has 26 options. We know that there's 25 options for each letter in the 3-letter word that cannot contain an A, since we subtract 1 from 26. Hence, there's 25 to the 3rd ways the Mongolians to create a 3-letter word with no A's.
Subtracting 25 cubed from 26 cubed gives us an answer of 1,951. Easy as pie. Now that we concluded our discussion about complementary counting, we have a problem for you to solve. This is problem 2.7 of section 2.3. The Smith family has 4 sons and 3 daughters. In how many ways can they be seated in a row of 7 chairs such that at least 2 boys are next to each other?
We will now discuss constructive counting. With this method, we think about how to construct an object step by step. Multiply the total number of ways to produce the item at each step.
To illustrate this idea, we will solve problem 2.9 of section 2.4. How many sequences, x1, x2, x3, all the way till x7, can be formed in which all the xi are integers greater than 0 and less than 6, and no two adjacent xi are equal?
Just like constructive counting suggests, we will calculate the number of possible integers that each xi can take. We know that 5 numbers can fulfill the conditions imposed on x1, as it can be all integers from 1 to 5, which is obviously 5.
We notice that x2 can take only 4 integers, as it can be every integer from 1 to 5, excluding x1. It becomes apparent that all integers x2 to x6 have only 4 options, as they cannot be the same as the preceding number.
Hence, there's 5 times 4 to the 6th power, or 20,480 possible sequences. In general, when we apply constructive counting, we start with the most restrictive condition of the construction first. In this problem, the fact that adjacent xi must not be equal is the toughest restriction. Looking out for restrictions is a good introduction to our last topic, counting with restrictions.
Let's learn this method with problem 2.11 of section 2.5.
The Smith family has 4 sons and 3 daughters. In how many ways can they be seated in a row of 7 chairs, such that all 3 girls sit next to each other?
Let's not worry about which specific order of boys and girls sit at which seat. Instead, let's only consider the ways in which the 3 girls can sit together. To visualize the ways in which this condition is met, let's denote each girl as G, and we'll pretend that they're indistinguishable, and the boys as B.
There's only 5 basic configurations of the boys and girls. G, 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 B, 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 G, 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 B, 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 G, 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 B, 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 G, 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 B, and B, 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 G, G, G. Why'd you make me say that? Sorry. Since there's 3 factorial orderings of the 3 girls and 4 factorial orderings of the 4 boys for each of the 5 basic arrangements, there's 3 factorial times 4 factorial times 5 total ways. This equates to 720 total permutations.
Since counting with restrictions is a common method of solving harder counting problems, it's imperative that you develop a strong understanding. Hence, we have a problem for you to solve. It's problem 2.13 of section 2.5.
The Coventry School's European Debate Club has 6 German delegates, 5 French delegates, and 3 Italian delegates. In how many ways can these 14 delegates sit in a row of 14 chairs if each country's delegates insist on all sitting next to each other?
Today was a very fast-paced lesson. As a result, feel free to rewatch certain portions of the video in order to develop a strong understanding. The solutions to all the homework problems will be presented in our next video.
As usual, please subscribe to our channel and share the videos with anyone who wants to learn.